If you have an n by n matrix A, then you can use that matrix to define a dynamical system. And the question that comes from that dynamical system is, how do you compute powers of A efficiently? You can also use that matrix to define a differential equation. And then the question is, how do you solve that differential equation? These might seem like two completely different problems, but it turns out that we can solve both of them using the same method. In this lecture, we'll begin the process of describing this method. First of all, some terminology. Two n by n matrices A and B are called similar if there is an invertible matrix P such that P inverse times A times P is equal to B. Now you might remember from earlier in the semester that this P inverse AP formula appeared in the context of change of basis. Basically, the idea is that if you have a linear transformation from a vector space to itself, and you pick two different bases for that linear transformation, then you can get two different matrices that are the matrix of that transformation with respect to the different bases. Those two matrices will be similar to each other. Now, what I just said is very conceptual, but there is a more down-to-earth way of thinking about it, which is that you can think of P as a change of perspective or like a translation from one point of view to another. So here's the picture of that. You have A and B, which are n by n matrices, and so you can think of them as linear transformations from Rn to Rn. And then we're thinking of P as being a translation from the B picture to the A picture. If P is a faithful translation, then that should mean that doing B is the same thing as translating and then doing A and then translating back. And that's exactly what the equation P inverse times A times P equals B says. Don't forget that from the point of view of linear transformations, you should read matrix multiplication right to left. So P inverse times A times P means that you do P, and then you do A, and then you do P inverse. So that's translating, multiplying by A, and then translating back. So what does this have to do with dynamical systems and differential equations? Well, with dynamical systems, you want to compute powers of matrices, and it turns out that similarity plays well with powers of matrices. Specifically, if P inverse AP is equal to B, then B squared is P inverse AP times P inverse AP, and the P and the P inverse in the middle cancel each other out. And what you're left with is P inverse times A squared times P. So this tells us that B squared is similar to A squared, and in fact it's the same P that translates from one to the other. And in fact the same thing happens when you look at any power of B. B to the n is P inverse times A times P multiplied times itself n times. And the P's and the P inverses in the middle will cancel each other out. And what you're left with is P inverse times A to the n times P. So what this means is that if you can calculate B to the n quickly, then you can use that to calculate A to the n quickly. All right, now let's look at what happens with the differential equations. What happens here is that the matrix P gives you a substitution that you can make where x is equal to P times y. If you want, you can think of this as a change of variables, but another way to think of it is that it's sort of like a U substitution, like in calculus. So the idea is that we're going to use this substitution to rewrite the differential equation in terms of y. So remember that in a U substitution, whenever you have some equation that relates x and u, the next step is to take the derivative of both sides. So we're going to do that here. And when we do that, we just get x prime equals p times y prime. The p is a constant matrix, it doesn't depend on t, so you can just pull it out when you take the derivative, and it's just x prime equals p times y prime. And then when you substitute those things into the differential equation, what you get is p times y prime of t is equal to a times p times y of t. And then, if we take that equation and we multiply both sides by P inverse, we get y prime of t equals P inverse AP times y of t. But P inverse AP is B. So the equation we end up with is y prime of t is equal to B times y of t. So in other words, the fact that A is similar to B means that we can do a substitution that turns the equation x prime equals ax into the equation y prime equals by. So what we found in both situations, dynamical systems and differential equations, is that if A and B are similar, you can rewrite the problem for A in terms of the problem for B. Okay, well, how does that help us if we still have to solve the problem? Well, it might help to go back to the u substitution analogy, right? So let's say you have some kind of an integral, you make a u substitution, and you rewrite the integral in terms of u. You still have an integral that you have to do. But the point is that you got to choose which substitution you wanted to do, and you wouldn't have made the substitution if it didn't make the problem simpler. And that's exactly what we would do here. So the idea is that given your matrix A, you would want to find a similar matrix B, which is simpler in some way, where simpler means that you can actually solve the problem directly. And so the question is, how do we do that? What do we mean by simpler? And once we know what simpler means, how do we find a similar matrix B, which is simpler? Well, for this purpose, the simplest matrices are the ones that are diagonal. And what that means is that all of its non-zero entries are along the diagonal. So here are some examples of diagonal matrices. And note in particular that it's okay for there to be a zero on the diagonal. What's important is that the entries that are off the diagonal have to be zero. So to keep things simple, let's focus on the 2x2 case, but everything we're going to do works in higher dimensions as well. So this is the general form of a 2x2 diagonal matrix. And we're using the Greek letter lambda to denote the entries along the diagonal. And my claim is that diagonal matrices are simple in the sense that you can solve the corresponding dynamical systems and differential equations easily. So for dynamical systems, we would want to compute powers of d. So let's start with d squared. You do this multiplication, and what you'll notice is that the result is again a diagonal matrix, and where the entries along the diagonal are just the entries of d squared. And if you keep multiplying out higher and higher powers of d, the same pattern continues. D to the n is a diagonal matrix where the entries are the entries of d to the power of n. And so this is great. You can calculate powers of a diagonal matrix easily. Now let's look at the differential equation perspective. So let's say we want to solve the differential equation y prime equals d times y. Well, when we write this equation out in coordinates, it looks like this. And so the resulting system of differential equations is y1 prime equals lambda 1 times y1, and y2 prime equals lambda 2 times y2. And what's great about this is that the system is decoupled, in the sense that the equation for y1 prime only involves y1, and the equation for y2 prime only involves y2. And so we can solve them separately. There's no interaction between them. And then the other great thing is that these equations are probably familiar to you from calculus. These are the equations for exponential growth. Specifically, the solution to the first equation is that y1 is some constant times e to the lambda 1 times t. And similarly, the solution to the second equation is y2 is some constant times e to the lambda 2t. Okay, so we'll come back to this later, but for now, the big takeaway is that diagonal matrices are good. We can solve the dynamical systems and the differential equations that come from diagonal matrices with explicit, simple formulas. Okay, so everything that has happened so far in this lecture is really just motivation for the following question. Given an n by n matrix A, can we find an invertible matrix P and a diagonal matrix D such that P inverse times A times P is equal to D? If you can, then the process of finding the P and the D is called diagonalization. If you can diagonalize A, then based on what we talked about earlier, you can use the P and the D to solve the dynamical system and the differential equation associated to A. So for now, we're going to focus on this part of the problem. How do we find the P and the D such that P inverse AP is equal to D? And then after we figured out how to do that, we'll come back and we'll use it to solve dynamical systems and differential equations. So let's look at what a diagonalization would entail. Well, that would mean that you have a diagram like this, where multiplying by d is the same thing as multiplying by p, and then by a, and then by p inverse. And now, let's say that d has diagonal entries lambda 1 to lambda n. And let's say that the columns of p are v1 to vn. And now consider the vector e1. If we multiply e1 by d, then we get the first column of d. But if you look at the first column of d, it's actually e1 scalar multiplied by lambda 1. On the other hand, if you multiply e1 by p, then you get the first column of p, which is v1. But if you multiply lambda 1 times v1 by p, then that lambda 1 can pull out, and you get lambda 1 times v1. And so, in order for the diagram to work, in the sense that P inverse AP would be equal to D, it's necessary that A times V1 is equal to lambda 1 times V1. And if we went through this same analysis for E2, E3, etc., we would get similar equations. A times V2 equals lambda 2 times V2. A times V3 equals lambda 3 times V3, and so on. So this kind of equation keeps coming up, where A times a vector is equal to a scalar multiple of that vector. And so it has a special name. It's called the eigenvalue equation. And you can see from the context where this equation appeared that what's happening here is that we're given the matrix A, and we're trying to find the V and the lambda that make this equation true. And when you do that, then the V is called an eigenvector of A. And an important caveat here is that V needs to be a non-zero vector. The zero vector doesn't count as an eigenvector. And then the lambda that appears here is called an eigenvalue of A. So we're going to talk more later about how to find eigenvectors and eigenvalues. But the key point now is to recognize that if we can find them, it gives us a way to do this diagonalization process. So if you look at the above discussion, you'll see that every column of P needs to be an eigenvector. And P should be invertible, which means that the columns should form a basis for Rn. So we need a basis of eigenvectors. But if we can do that, then that's enough to diagonalize the matrix. So here's the result stated as a theorem. If V1 to Vn is a basis of eigenvectors of A, with corresponding eigenvalues lambda 1 to lambda n, then if you set P to be the matrix whose columns are the eigenvectors, and you set D to be the diagonal matrix where the diagonal entries are the eigenvalues, then that diagonalizes A. And the cool thing is that the analysis that we did at the top of the screen proves that this works automatically, so we don't even have to multiply P inverse times A times P. We don't even have to find P inverse, which can be a lot of work to find the inverse of a matrix. We just automatically know that this will work. All right, so just to give you an example of this in action, let's look at this matrix. We're going to talk later about how to find the eigenvectors and eigenvalues, so for now I'll just tell you what they are. So here they are, and I'll point out that even though you don't know how to find them, you do know how to verify that they're correct. All you need to do is multiply A times the vector and check that you get the same thing as you would get if you multiplied lambda times the vector. So for example, if you take A and you multiply by V1, and if you actually do the multiplication out, you'll get 2, 2. And 2, 2 is 2 times 1, 1. So it's true that A times V1 is equal to lambda 1 times V1. And of course, you can do a similar check for V2 and lambda 2. So once we accept that these are eigenvectors and eigenvalues, and it's clear that V1 and V2 are linearly independent, and so they form a basis for R2, then everything else comes from the theorem that we just looked at. So you set P to be the matrix whose columns are V1 and V2, and you set D to be the diagonal matrix whose diagonal entries are lambda 1 and lambda 2. And then the theorem tells us that P inverse AP is equal to D. It's probably a good exercise for you to multiply it out and check that it works, but it isn't necessary to do that because the theorem tells us that it will work. So as I mentioned before, we'll be able to use diagonalization to study dynamical systems and differential equations. We'll talk more about that later, but just to give you an idea, here's a simple application. Suppose we wanted to find A to the power of 50. Well, One way to do it is to multiply A times itself 50 times, which is a lot of work. But another way to do it is to use the diagonalization that we just found. And the way to do that is we can take this equation, P inverse AP equals D, we can multiply on the left by P and on the right by P inverse. And then on the left side, we get cancellation between P and P inverse. And so we're left with the equation A equals PD P inverse. So what about A to the 50? Well, as we discussed earlier, when you take powers of similar matrices, those powers are similar, but with the same P. So that means that A to the 50 is P times D to the 50 times P inverse. And what's cool about this is that we actually know what all three of those matrices are. Of course, we know what P is, and then because D is a diagonal matrix, D to the 50 is just another diagonal matrix where the diagonal entries are the entries of D to the power of 50. And then note that minus 1 to the power of 50 is just plus 1. And then, to get P inverse, we just use the 2 by 2 inverse formula. And so now it's just a matter of multiplying these three matrices out. And when you do it, this is what you get. And there you have it. It's a nice little formula for A to the 50. It's not super quick, but it's a lot better than multiplying A times itself 50 times.